Hi, folks. I wanted to show you this little example here about the additive synthesis of basic waveforms. All right, so I prepared this little example here. It looks complicated, but it's not. Let me just walk you through this whole example. So I first take one base frequency here, and I multiply it by 1, which is meaningless, and that determines the frequency of oscillation of this object here, and then I divide it by 1, which is also meaningless, and then I select one of the two outputs. That's what this does. But now here on this second one, I multiply the frequency by 2, and I divide the amplitude by either 2 or 4. And I keep doing this. I multiply the frequency by 3. So these are all harmonic partials, which I divide by either the same number that I multiply it to, or I divide it by its square. So having our last meeting in mind, you see that I'm about to create here either a sawtooth, or a square wave, or a triangular wave, in which the squares here are needed for the triangular wave. Okay, I probably shouldn't need to, to have the 4 squared and the 2 squared, the 4 squared, and the 6 squared, since we're not going to use even partials for the triangular wave. But anyway, just for the sake of completeness, I put it there. Now this is an object called the matrix, in which I can, let me show you how it works. I can select which partials I'm going to turn on and off, right? So this means I'll have just these 3 inputs on, and so on. You hear it, okay? Now here I have a volume, so we don't go too loud when I turn on the audio, which I can do right now. And I need to specify a base frequency. Let's just get 440, just because we are so used to it. And then this is a little menu here that selects this little box here addresses the selector objects there, right? So I can choose to have these squared outputs, or I can choose to have only the regular outputs, or I can have them all off. And here's this is just how quickly Max plots the output of this thing. I found that 301 is a good number for this. So let's go ahead and oh, by the way, the very last thing we need I wanted to tell you is that this is how I displace the phase in each of these sinusoids, right? So remember from last time, phase here in Max runs is normalized, so it's divided by 2 pi, so it runs between 0 and 1. So this means that to get all cycle objects in Max are cosines by construction. So if we want to have a sine, we need to have a phase displacement of 0.25, or a quarter cycle. Okay, so let's turn this thing on, and well, the first thing we need to. So I want to get a sawtooth out of this. Okay, so now this is on, and we're not hearing anything because the matrix object is not producing sound. But let's have the first partial here. So here's the first one, and it's just a sine. Okay, and the transitions, when I turn them on and off, they're a little abrupt because, yeah, this is just a demonstration. So this is the second one. So it's already half the amplitude of the first one, right? Let me make this, yeah, make it louder, but I'll turn down the volume here if this gets too loud. Okay, and then the third one is already a third of the amplitude, and a fourth of the amplitude, and a fifth, sixth, seventh, and eighth. Okay, and here is the case where I divide things by the square of the harmonic partial. So big. So now this is a lot smaller already, and a lot smaller. So the last one is almost, you can hear it, but you almost can't see it. Okay, so according to those formulas that I gave you last time, let's find those formulas again. This is my PDF of the whole thing. I think it was right. Yeah, right here. Let me hide this thing. And so these were the formulas, right? So in here we sum to get a sawtooth wave. We need sines, and we need the sines to be divided by n, where n is the integer that determines each harmonic partial. So how do we get this here? Well, to get a sine, we need to displace it by 0.25. So now these are all sines. And divide by n. So when I start adding things up, you'll see that this thing is going to converge actually quite quickly to a sawtooth wave. So if I keep adding harmonics like this, you're going to get almost a straight line there. There will always be ripples. So what if I wanted to have a square wave out of this? Remember, square waves, by the formula here, are basically the same procedure that we do for a sawtooth wave, only with odd partials. Remember, I told you that if you get the index 1 here and you multiply it by 2, subtract 1, you get 1, and then you get index 2, multiply by 2 is 4, minus 1 is 3, and you keep going, you get 1, 3, 7, 9. So you get only odd partials here. So sure enough, when you only add odd partials to this thing, right, it starts to form a somewhat square shape there, right? And you see this sound that already resembles a little bit of a clarinet. And in order to get a triangular wave, we divide by the square of n. So here we start dividing by the square of n. Obviously, if we add all partials, we don't quite get what we want, right? So in order to have a triangular wave, we only add odd partials. Okay, and it starts converging pretty quickly. However, in this case, if you remember the formula here for triangular waves, we actually use cosines. So that's why they sound like a triangular wave, but they don't look like one. So here, if we just change the phase back to 0, we'll get the triangular wave. Okay. So triangular waves actually, because they don't have the same type of discontinuities of a sawtooth and a square wave, they actually converge to that shape much faster. Okay, you see already, you're getting the shape out of the third harmonic. If you add 10, 15, 20 harmonics, then obviously minding the Nyquist frequency, you see that it will get a triangular wave very fast. Okay, that was it. Thank you guys. Bye-bye.